Hello class, Dr. Mike here for our Network Security or Security Plus course, CIS 2640. This is topic 3, Basic Cryptography, mapped to the current textbook, currently chapter 3 of this recording. And next week after that is Advanced. I'm going to go and put this out now. Basic and Advanced. Don't worry, Advanced is not this. We're not going to be doing any big math. Really what we're looking at is basic cryptography is sort of the basics of it, and advanced we're going to look at implementation, how it's actually used. So in case basic cryptography, again I'm using the textbook slides, but I'm definitely thinned them out, but we'll look at the summary when we're done to be sure we covered any important items. So again, basic cryptography, again, what is cryptography? Scrounging information, right? So it cannot be read unless someone has the access to it, some sort of key or some sort of knowledge of how it was scrambled. Another aspect is stenography, which you actually, I think you see in one of the labs, is you can hide data inside of an existing item. The biggest one is like hiding a text file in an image, or secret text in an image, or hiding stuff in metadata, things like that. So some key terms here again. Encryption itself is the process of taking plain text and making it into encrypted text. Decryption, of course, is the opposite. Ciphertext, just another name for the scrambled output. Clear text, of course, is the term you'll see used for plain text. So the plain text itself goes through some sort of algorithm, usually called a cipher. And it uses some sort of key in place. And the keys nowadays is typically mathematical, but it can be all kinds of things. One of the basic ones is substitution ciphers. So, or a Caesar cipher in this example. So it's not always mathematical nature, even though everything does boil down to some sort of shift, in this case a shift of X, maybe 3 letters shift. But example, cryptography's been around for a long time, and there's actually been evidence of this right here. Of Roman soldiers writing messages with a stick of a certain length, a certain diameter with so many sides. You can write them out, then unroll that piece of letter there and send that along with the messenger. And unless the receiving party knows the length, diameter, and number of sides to unwrap that, and then they can read it. So again, there's ways that even back in the day they used to go ahead and sort of scramble information. So substitution ciphers, Rod 13, Caesar ciphers, again, and an XOR cipher. This is using the XOR or basic our logic basics to either compare 2 bits and either flip a bit based on the one or the other being on. So cryptography basically is just this. And we're going to come back to this a little bit, is with plain text, some sort of encryption algorithm, we have ciphertext, and then to decrypt it you need to have the key to decrypt it. Now there's a couple aspects here we'll look at. One is public and private key cryptography. But in any case, modern cryptography itself does rely upon mathematical formulas as the basics for the algorithms. I'll say this, it's probably in the textbook too. If you go to a place as a cybersecurity engineer, analyst, whatever the role may be, and they're making their own cryptography, that's usually a bad thing. We do not like to roll your own cryptography. Basic cryptography, mathematical algorithms go through years of proofing through actual mathematicians. So in any case, just a heads up there, if you see someone saying, well, we would do our own cryptography, that's probably bad. Another thing too is this actually relies upon random numbers, randomness. So cryptography itself, mathematically, whether the encryption may be, when we have our key generation, so we have our key. This key could be seeded with a secret phrase or password or passphrase. But also it can be taken from a large pool of random numbers, zeros and ones, randomness. So how do we create randomness? This is actually, I always find a fascinating aspect for this. And by the way, let's look at some terms here. This chunk of randomness, you pull out a part of it to create your random key. So normally this is called a number used once or a nonce. So you use this pool of randomness. I mean, after you create the key, you throw this away, and you generate, and you get another pool of randomness for your next key. And after it's used, it's thrown away, and so on. So you try to use this once, hence numbers used once or nonce, number used once. Randomness is a fascinating topic. I always found it fascinating because of this. How do you get something random from a computer that is not random at all? Computers and software are very much structured. You know, you run at a certain megahertz, a certain fetch cycle. Everything's very clockwise state. So how do you get something random from that? Definitely look at things like random.org. Some really great stuff here. Both are just tools to get random numbers, even just for a game. To randomness used for encryption. So, and there's actually a distinction there. So if I have a game and I need a random number between 1 and 100, most of the time any software that generates that random number is fine. With the underlying software library, it could be just a random number, like a Python net random library. That works fine for that reason. But for encryption, you got to make sure that it cannot be traced back. There's actually ways to go and detect patterns for this. And this, again, this article on random.org talks about PHP on the PHP random library on Microsoft Windows itself actually has a pattern to it. Those can be tested for very easily, actually. All places you might see randomness might be a random session ID, which you think is random, but you find out actually uses a date timestamp. So tools like Burp Suite can check for this randomness in cookies and session IDs. So if it could be guessed, then it could be hacked. So in any case, the chapter talks about that. Again, I think a pretty fascinating topic. Ram.org actually a great site too, so to look at more in the details about that. Some important stuff here. How can we use randomness? It's used in a lot of areas. Definitely mostly is, of course, confidentiality. Again, the idea being only the party I want to view this protected text, my ciphertext, they have a key for it. Integrity. Again, we'll show you where we can use this to actually see and verify. So there's actually integrity checks that use encryption algorithms, and we'll talk about that in a second. Authentication. Again, we can verify who someone is. We'll see this in the next chapter, but we see with certificate authorities. How can I ensure I'm actually at google.com or I'm at sinclair.edu? So there's ways for this part of our authentication and verification process. Non-reputation, to prove that someone did something. So almost like a blockchain in a way. And of course, obfuscation, we can make something unclear. This is really sort of just a way to remove something. It's not really encryption per se, but it is a way to, it's sort of like a little encryption light. Not the best way to protect data, but it is part of a process if we're doing maybe like code protection. Also, if security through obscurity, this sort of comes in obfuscation. Again, make something obscure isn't really full protection, but it is something that can be used as part of a protection plan. So where do we use our cryptography? And this is pretty important. We're going to see this definitely in the next chapter, the next topic, which is more advanced cryptography. So data in use, data in transit, and data at rest. So let's start with data at rest, our database. Do we have encryption for key parts of the entire database? And it can be just data itself. It doesn't have to be a database. It can be a file system. Or maybe the data is stored in a certain condition and that is encrypted. When it is sent up for processing, it is also done in an encrypted manner. And when, of course, it's sent across the web, let's use this here, to maybe just someone's mobile device. this transit here is also encrypted. So we offer encryption through here. So again, I don't want, we'll leave it at that. Those are 3 areas to look at when evaluating the cryptography used, either as your target or if you're at a company and you want to evaluate your security. And we're going to talk about, the next chapter goes into more detail on all 3 of those areas. So constraints, of course, there's constraints. One of the biggest one would be back in the day, years ago. The act of encrypting would be CPU intensive. Also, encrypting, decrypting network traffic was not very viable. So there would be you would decrypt at the network edge, and everything internal would be decrypted, for example. Our actual devices now are very powerful, and even modern cell phones could do very advanced cryptography on the fly. We have hardware also that helps with that. So keep that in mind. So now, how is something encrypted? So the encryption process itself does not depend upon not the actual algorithm, how the algorithm does it, which is the mathematical part, is how we take the actual bits. 3 things here in 2 areas actually are, we have block ciphers and stream ciphers. So the block cipher itself, basically we take in with our stream cipher, and this is, think of the term stream here. Let's change our text size here. Yeah, we'll turn to Sprint ink. So our stream cipher itself, it's going to take in the 1s and 0s as they come in, and it'll encrypt them on the way out. It's pretty straightforward. Think of it that way. It's just we are encrypting the stream of 1s and 0s. So again, we can have our plain text here. It comes in, and we have our cipher text, and the key here, of course, is what tells it to either change or not change that. So pretty straightforward. Block text. Block cipher is that it takes a block of data and encrypts it at a time. So let's go ahead and close that. So again, block cipher and stream ciphers operate a little differently. Sponge functions, sort of hybrid between the both. So where stream cipher takes 1 character at a time, replaces it with another based upon the key and the key and of course the encryption algorithm. The block cipher will take a block of text. Now that block is of a set size. A sponge function really could take any various size and sort of block it. So it sort of can take a block of 2, 3, or a block of 128. So in any case, this is how we have our basic encryption is ran. The categories of encryption. First, let's talk about symmetric and asymmetric. We're going to come back to that in a second, but we're going to talk about hash algorithms. So I mentioned before that we can use encryption in verification. It's used in a lot of places. It's used in forensics, where we create this digital fingerprint. And this fingerprint digest is usually called a digest or a fingerprint. It's called a hash, a file hash. And this is used again to verify that something has not been changed. So one simple way you'll see this, of course, you might see this even as an end user, is you download something and you call it a workstation hash or MD5. So you can see here, this is a download for the SANS CIF workstation for this file right here, which is pretty big. And the idea is if I download this large file, I want to make sure it is intact, it has not been modified, either maliciously or just from network issues on disk. And so it is, when it was generated, it was this MD5 was created. You can see there's the hash right there. Now the hash is one way, unique. You cannot tell what was inside of a file based upon this. And changing the file in specific locations does not change it at specific locations here. So it's like the beginning of the file has been changed, it changes here, or the end of the file. So we'll see that these hashing algorithms do have certain things. They're fixed size, unique, original, and they're very secure. MD5 is one of the common ones. There's SHA 128. 256. You can probably imagine that's the larger the hash, the more accurate it is, and the less chance it has something called collisions. But you can see here I downloaded this file, and you can see I did MD5 on my CIF workstation OVA file, and I have the hash. So it matches, so I can verify that this OVA file is good, so I know I can now use it. So use for integrity, definitely, and a great way to verify a source has been downloaded. Again, you can see here in this slide deck, they'll give the SHA-1 in this case. So make sure that if you do verify, use the correct tool. Command line has a lot of tools. There's Windows tools that will hash a file and give you several SHA-1, MD5, SHA-256, 128, give you all those. And again, you can verify that this 2.9 gigabyte file is intact. So a very handy way to verify stuff. And I talked about this already. There are also other ways of hash algorithms. Race and integrity primitive evaluation message digest. We have those, and we have the HMAC. Some use secret keys, some do not. Let's talk about cryptography itself. So first off, the algorithms themselves. I know this is probably in a slide, but where do these algorithms come from? So NIST is a great source for this, and there's actually a cryptographic standards guideline. So which one should you be using? So a lot of software-based. When someone creates a piece of software that uses cryptography, you should verify that they are using NIST approved functions. So you can come here and you can see what are the approved functions, which ones are not approved. There's some have been discontinued because of either collision issues or just weakness now. So key management, key establishment, key management guidelines. Again, I don't want to read all this to you. There's always SP documents. How do you manage keys? The idea here is you don't have to come up with it on your own. There are guidelines for this. NIST is definitely a place to go for this. So make sure that, again, if you implement software from a vendor and they say we encrypt, you say, well, how do you encrypt? Well, we use the Java, approved Java, encryption libraries, and here's the libraries we use. Those libraries are then more approved and should read back to approved NIST, approved guidelines here. Sorry. So again, I'm not going to read NIST to you, but definitely a good resource. Have NIST in your bookmarks. We did some common encryption algorithms: DES, triple data, or TES, triple data encryption standards, AES, and a bunch of other ones. Again, this dictates this algorithm here and our key generation. So an important point here, if it's not in the slide deck, is if the key generation is based off some sort of passphrase. If it's a weak passphrase, it's going to be a weak key. So I don't want to create an encryption key that says, based on the word password, and then have it use weak or old encryption algorithms and hence have a weak key. So I'm not going to read this to you. Go through the chapter on these. DES, TES, they use a certain size key, they use a certain size block ciphers. Some use extra multiple rounds of encryption. Triple DES will take the same block and encrypt it 3 times, like you can see here. And so we'll have different ciphertext and even different keys. So there's triple keys, 3 keys. Think of it as locking something 3 times. So you can imagine the more keys are used, that's more key generation, that's more, and of course more encryption is more CPU power. So triple DES is great for like disk database. That's that data at rest. We have a lot more CPU power that can impact it. Where data in motion, you got to have a different play. So AES, again, NIST approved. Look for NIST approved. 128 bits of plain text to block. Blowfish, IDA. Again, at the time of this recording, and then the slide deck here, this can always change. So don't take this presentation and what I have on the slides here as current. These can change. So, all right. So, what do we have here with keys? So, when we get into keys, this is what I'm just going to show you here. We have something called symmetric and asymmetric key encryption. So, symmetric is pretty straightforward. The idea here is this key is generated using hopefully improved encryption algorithms. And to decrypt it, you need to have the same key. Well, this is fine for maybe, again, for data at rest, right? Or even data in processing where a certain key is used, the same key is used for both encryption and decryption. So if I was to make some ciphertext and share this with an outside source, I would need to share this key with them. And this is fine. Again, this actually lends itself to become very powerful encryption. I can use that triple DES with a symmetric key. Again, by example here again, we'll come back to a second. This is asymmetric. So, but what if I get to the point where I need to create a lot of keys? And so key management is definitely an issue. So if I have a single key, if I have key 1 and I use it to encrypt this ciphertext, I share this ciphertext with X parties, right? I need a shared key 1 with all of them. Well, what happens if key 1 gets leaked? You can see the issue here, right? And also, this is not manageable. If I this does scale up. If I get, from 1 to n key sharing, well, if key 1 itself, I can't scale key 1. If I need to create another one, if I need, create 10 of them, 20 of them, or share them, we have a lot of issues with key sharing. So with 1 or 2 people, maybe it's okay. But when it comes to actual things like encryption over the web, we use something called this. We use asymmetric or public key encryption. So what this comes down to in this slide, and this to show you is, we actually do create 2 keys. And we create a public key and private key. And it's done with a lot of different functions, but the biggest one is when we do key generation, we use a random number, and we actually use a prime number, or a series of prime numbers. And what this really means is this. So I myself, again, I have a private key, and I have a public key. Private key I keep secure and all to myself. Public key I can share. So think of it this way, instead of sharing the key, I'm sharing a lock. And so you want to send me something that only I can decrypt. So you take my public key using this key, and usually we're going to look at RSA. That's actually the big one. RSA is what's commonly used for everything. RSA encryption will say, all right, I'm going to take that public key, I'm going to encrypt data with it, but it can only be unencrypted if you have the private key. So it's it's a pretty big breakthrough. Before we had this public-private key and RSA. Without this, you don't have online banking, online shopping. You don't have the ability to actually generate public keys on the fly. In fact, I can create this key set as many times as I want, and it's not uncommon to create a public key for one-time use, sometimes for when you do online shopping. So this breakthrough again with public-private key encryption came through RSA. And RSA is, and I forgot it, RSA is the initials of the 3 individuals who created this algorithm. But there are different ways to do RSA. There's a DSA, and there's things related to how we share the keys. So you can verify the key I'm given, verify this public key that I'm given is Alice's public key. So there's actually encryption for that too. So DSA will help us ensure that the key is correct, but RSA and elliptical curve cryptography is another way to do sort of create this public-private key pair a little more efficiently on the CPU. So, so again, published in 1977 by MIT. Again, I don't put the names of the 3 individuals there. I should head that up. Uses 2 large prime numbers. Again, in this large prime numbers, these come from random number pools. Hence, this goes back to my previous thing about randomization and having large amounts of random pools of data of nonces you can use once. So you can read in the book about elliptical cryptography. Just a way to take a few points. It uses a different way, sort of this curve in math, to create all those random numbers that's used in key generation. DSA is how we verify, again, how we verify the key is from who they say they are. This is not too different from what you get with certificate authority. So I can verify, that it's, this verification you see in your browser a lot of times here. The certificate, it's really the same thing. And this is where we're going to talk about this in the next topic chapter, which is advanced or implementation of cryptography. But it is the same thing. It's DSA is used to prove and verify that the key. That way, I know this key, I don't get a fake key that gets, I'm given private information to what I think is Alice is actually not Alice. And I can verify it's Alice's key. So again, and this key exchange is pretty important to how we exchange keys. Sometimes we'll actually have a ephemeral key, a temporary key to create a temporary connection to exchange our public keys that might be only used once, that can only be decrypted with a private key. So, and there's different things here. Look in the textbook. Diffie-Hellman, definitely important. This Diffie-Hellman is one of those ways that we use in our key exchange. And perfect forward secrecy. Look at that too. It's in the textbook. I'm not going to read the textbook to you about that, but it's important to understand how that works. It's not always used all the time. That's really for high secure web traffic a lot of times. So again, we have some ways we can do cryptographic attacks. So one of the biggest one is the target itself, its algorithm. Known ciphertext, known plain text attacks. Really what we do is we can understand the encryption. Hence, if I can go in and feed in a known phrase, hello gets encrypted with a certain key. Well, it's going to have a certain output of ciphertext. Well, if I can guess this, then I can guess the key. Now, this is not very easy to do, but it can be done as was done in the past. In fact, World War II, the Germans used encryption, and they always ended their communication with like Heil Hitler, I believe it was, or something like that. And the end of the ciphertext had the same exact key block, and that could land. So you always knew the same word was at the end of the message. Well, if knowing those two pieces, you can determine the key. So even back World War II, though, they changed keys every 24 hours, but they were allowed to using. Because Alan Turing and his invention with the bombas, it's a great story, to determine the keys based on that fact. So that's the one thing. Known ciphertext, downgrade attacks. This is done over the web. A web browser will communicate and say, "Hey, what kind of encryption can you use?" And normally, the return is, "Well, I use these. I can support these encryption algorithms, the best to the least." Most of the time, your browser will ask for the best encryption because you want the best security for your browsing, your transactions with the web. But you can, actually tell it I need the weakest, and so make the target use the weakest encryption. So the idea here is they try to support many web browsers. And doing that, they do allow weak encryption, so you might be able to exploit that. Biggest thing is to, after a while, you have to deprecate, like supporting IE6. I worked at a place where they kept IE6 support around because the customers still use it in some places. They don't want to upgrade. They had to use it or whatever reason. So you could definitely exploit that. Bad ciphertext, null ciphertext. If I can inject something with null values, we saw this, and a few years ago there was a WPA attack where they were zero key insertion attack. So there's downgrade attack there. Just using bad algorithms. Algorithms, you know, this goes along with software updates, middleware updates. You know, someone using old algorithms are known to be weak. And of course, bad implementation. Again, maybe someone's just not doing the key handling incorrectly, or they're doing bad key generation, or they're not using good randomization in their nonces. So, collision attack, you can see that there is a chance for collision. This really comes with hash functions. This idea is a larger hash is better to use, but there's a chance of that. Again, use of cryptography. Again, I'm going to really look at this a little more in depth when it comes to the at rest, in process, and in transit. But again, encryption in files, encryption on hardware and software, I mean, can be applied in a lot of places. A lot of modern operating systems will encrypt drives. Your mobile phones nowadays will actually encrypt, you know, right there, encrypted on the device. So make sure it's being used properly. There's also tools you can use for doing your own encryption. PGP's got some great encryption utilities. And you can do file and system encryption on the operating system itself. Again, we see here full disk encryption with BitLocker and other OSs. So hardware encryption, sometimes you actually have a device. This is called a trusted platform module. This is a chipset usually on most modern systems that actually will create and or either do key storage, key handling, or create that randomization that you can't get from anywhere else. So that TPM, trusted platform module. And of course, probably with this slide is mobile, you know, external hard drives, external USB keys. If there's anything on there that could be of sensitive data, you should use encryption there too. So talked about it already. There also are hardware security modules, larger stuff here for like our network. Again, this could be actual entire rackable units. They could be part of an existing hardware server and or network hardware you buy. So make sure that those are, again, those are the kind of things you want to audit and verify work correctly. So in any case, that should cover, that covers our chapter summary here. Again, chapter itself is going to go into some details I probably didn't go over. Probably some good examples in there too I didn't talk about. I think we covered most of the good stuff. Yep, I think we did. So that is basic cryptography, and I will look forward to advanced cryptography next.